So, continuing from where we left each other in the last lecture, wherein we discussed Aristotle and the concepts of motion at that time, and then I introduced to you Galileo in his law of inertia, which I will try to elaborate a little more, although the inclined plane experiments of Galileo I discussed before, where there was a concept of a positive acceleration and negative acceleration and then a zero acceleration. And then I talked to you about what is zero. Zero is a crossover from positive to negative or from negative to positive. So you find that if a body is moving in a motion and it has been given a velocity in this direction, and even if there is no force, the body will continue moving like that. This was one of the experiments that was discussed by Galileo. And so, because we are talking about laws of motion, and laws are something very dangerous, therefore the choice of the words that we use for the laws must be the correct set of words to define the things correctly so that no other meaning can be given to it. So I just say that before Galileo, the concepts were such that heavier bodies fall faster in proportion to their weight, and always a force is required to make an object move with a uniform velocity, moving in a straight line with a uniform speed. So look here. One of the words that I need to emphasize here is the word weight. The word weight actually is different from what we define as mass. Actually, weight is the force of gravity on a body in the downward direction, and is actually equal to m into g. If there is a mass, the mass is m, but the force on the body is what we call the weight, and this weight is equal to the downward direction. This is m multiplied by the gravitational field or acceleration due to gravity, as we say in common language. So this was one of the concepts, that heavier bodies fall faster in proportion to their weight. Now, Galileo, in his experiment from the Leaning Tower of Pisa, when he dropped two stones from the same height simultaneously, he found that the two stones, one a very light one and the other is very heavy one, both reach the surface of the earth in the same time with the same speed. They could see that was visible, and he showed that it's not the heavier bodies that fall faster or lighter bodies which fall slowly, but the two bodies are independent of their masses or their weights. Well, in the due course of time, when you go ahead and study about the fall of a body, and the fall of a body, we can do an exercise. Suppose you just think it over, that there is a set of clouds, and a drop starts from the cloud and comes down to the earth, falling straight away. And the drop mass is maybe 1/10 of a gram or like that. And if it is allowed to fall through 2 kilometers, and that is 2000 meters. 2000 meters. So you know that there is a relation, like you apply that, V square is equal to U square plus 2AS. If we do apply this relation, then we find that the drop starts at rest. Its velocity, initial velocity is equal to 0. So the final velocity that turns out to be is equal to V squared, gives it is equal to 0 plus 2 into G, which I take as 10, and S, which is 2 kilometers or 2000 meters. Then okay, I'll not take the meters, I'm making calculations. So this turns out to be equal to 20 into 20 into 10 into 10. 20 into 20 into 10 into 10. I'm being smart, and so you must be, because I want to find out what is the under root of this relation. And you know how much it is? This is equal to 200 meters per second. The velocity. The velocity, this, so V becomes equal to 20 into 10 is to 200 meters per second. 200 meters per second is a tremendous velocity. And if this drop falls with this speed, with its mass, then maybe it is going to put a dent on my hand. Okay? And it may even pierce the head. But it doesn't happen. Clouds are 2000 meters up, and the drops are dropping, have been dropping for millennia. So what is it? That this drop, which is much less than 1 gram, falling from a height this, and of course there is no question of what is the mass of the drop, but the body which is falling through in the atmosphere from a height of 2000 meter, it reaches a velocity of 200 meter per second, which is almost the same velocity which you get from the nozzle of a gun. Okay, so that means that this is a tremendous velocity. But what is the fact? The fact is that the drop is not dropping at this speed. These days you know that there are skyscrapers, drops are dropping. Suppose you are on the 70th floor and you are on ground floor. What do you think will be the speed of the drop while it's falling like this on the 70th floor and at the ground floor? Will it be more at the ground floor and less at the 70th floor? The answer is, it will be the same on the ground floor and it will be the same on the, if we observe it and make an experiment, we find that on the 70th floor, which is about more than 200 meters above the ground level, okay? So 200 meters above the ground level, the velocity is of fall is the same as the velocity of fall over here. What does that mean? It means that the body is not being, the raindrop is not being accelerated. So why? Why does it not? Because during the fall, if it were uh, not on the surface of the earth. If air were not present, then maybe its velocity keeps on increasing, and what we have made a calculation over here may be true, but after a small, as it drops, so there is a drag. The air applies the force, and there is one position when the terminal velocity is achieved. I'm just saying these things because you can make calculations, because you have learned about the kinematics. So that means, does the acceleration due to gravity fail? No. The acceleration due to gravity remains the same at the 70th floor as at the ground level. But the fact is that the net acceleration on that falling body becomes equal to 0. A velocity which you call terminal velocity. And it is found when we calculate the terminal velocity. Please go and refer to terminal velocity, try to calculate that terminal velocity, and you find that the terminal velocity depends on the weight or the mass of the body. The weight or the mass of the body. So if we do this experiment, if you go for that, what we will say today? That a heavier drop is going to achieve a larger terminal velocity, which means larger distances are travelled in the same interval of time as compared to for a smaller drop. So think, my dear friends, that what was wrong with the concept of Aristotle. I said I am not a chamcha of Aristotle, but Aristotle's theory that heavier bodies fall faster than the lighter ones, it appears to be true. Like another thing, today you have many pools, and you conduct that experiment in a pool. The Leaning Tower of Pisa experiment, like Galileo did there, then you will find that a heavier coin will fall faster as compared to a lighter coin, or a ball heavier in mass or weight will fall because there is a upthrust. So that upthrust, so in a way, what was observed and what was done by Arastu and his friends, his followers, the descendants, that was that they could think of the motion and they could describe the fall in the presence of a fluid, and that fluid can be a gaseous system, or it could be a liquid system. Okay, so there is viscosity and all those things, all those factors will come to you because you are an inquiring mind. You are the common person who has the guts to inquire. And then we find that maybe Aristotle was not very much wrong, but then we should appreciate the beauty of Galileo. The beauty of the law of inertia that was proposed by Galileo. Because Galileo proposed and obtained the results experimentally, demonstrated it, because the air density was not too much. It is not too much for a leaning tower of Pisa, which is not very in height. It is even less than the height of Qutub Minar in India. So for this short distance, he dropped the two objects, the heavier and the lighter one, and he found that they reached the same place, the place of fall in the same time. And so he could say, and people believe that, oh, heavier bodies do not fall faster. Heavier bodies do not fall faster, and therefore they said that, well, whatever we have had so far, it's all wrong. Okay, friends, the beauty was that Galileo could suppress the presence of atmosphere over there. And Galileo's theory is, there is an experiment in the books which shows that a heavy ball and a feather, they fall in the same amount of time if a good vacuum is created and the density of air is minimized. So in a practical situation, the beauty is that we can see the things separately, and a mechanics has to develop after Galileo dies and Newton is born in the same year. So Newton's law of gravitation came. Now what was proposed? Proposed was that when no force is exerted on a body, when no force is exerted on a body, which I will read it like this: when no net force is exerted on a body, forces may be exerted. For example, if I have a body on top of a table here, okay, this is the rigid body, the table, and I have a body over here, which I am showing to be in the shape of a ball. Okay, now this is at rest. I say this is at rest. When you look through the camera and you find it, you will say that it's at rest. But look here, my dear students, that you will also say that since this is the horizontal surface on the center of this ball, there will be a force mg towards the surface of the earth. Okay, this force is being exerted by the gravitation of the earth, and there, because it is at rest, because there is yet another force, and which we call in our junior classes, we were told that this is the force of reaction of the table on the ball. Now what is the force of reaction? This is a gravitational force. And what is the force of reaction? Think and think and think. This force is the manifest of electromagnetics. Electromagnetics. This one is a manifest of gravitation. And the net force acting on this mass or body or whatever you want to call it, a book or so, so net force acting on it is equal to 0. So I was here, and now I can say when no net force is exerted on a body, like in this situation, so there is this mg and there is this force r. Both are vectors, equal and opposite. They cancel out each other, and the net force on it is equal to 0. So when I say when no net force is exerted on a body, the body stays at rest or it moves in a straight line with constant speed. Okay, this is what was proposed. This is what was thought about. So there are two situations. The situation to realize is the position of rest, which we must understand very deeply, and the position of uniform or condition of uniform motion. Both these things are being addressed by the concept of the force, which is, that is why we say that the force which is able to change the position of rest or the position of uniform motion, as is the statement of inertia, okay, we'll say that this is the job of the force. The job of the force is to change or to try to change the condition of rest as it exists in the inertial frame of reference or of uniform motion, which also exists in the inertial frame of reference. Okay, what we require is a force. The job of the force from this law of inertia, which is also the statement of the law of inertia of Newton, which is known as his first law. Okay, this is what I explained. And then Galileo did a experiment on a pendulum, and he said in a pendulum, the pendulum has a position of rest, a position, a differential position where it is at rest. When it is removed in one direction to a certain height and then released, then the pendulum moves like this within equal intervals of time. It reaches from one end to the other end, and if the same is done in a bowl, we take a bowl, the second experiment of Galileo, and the same motion is repeated over there. In the third case, what Galileo said, he again argued from the inclined plane experiment that if I have an inclined plane, then I have a horizontal plane, and then suppose at this point I have another inclined plane, then my ball reaches the same height. You can read that in the book. It reaches the same height from which it was released, under the circumstance that the frictional force is very, very small. But if the inclination over here, the theta value is reduced and reduced and reduced, then what happens? That the same height is obtained after traveling a longer distance. So he argued that suppose there is the slope of the incline is equal to 0, tan of theta is equal to 0, then he asked a question: where will the ball stop? Because the ball has to achieve a height equal to the height from where it was released. Then, while working these things, came the concept of inertia, and it was found that massive objects possess more inertia than lighter objects. Okay, so the inertia of an object is manifest by the element which is known as mass associated with it, and I'm just giving you a hint that if you are home and you have work to do, go to the school, this, that, and early in the morning your mother comes to you, okay, some of you have that emotional mass less than the emotional mass of others. So if you have less mass and your mother says, "Utho lal, ab aankhein kholo, pani lai hu muh dholo," so you just get up and do it. Else what happens? The mother has to pull the whatever you are sleeping with, give you a slap or two. In that case, of course, your inertia is more because your kahili is more. Okay, so it is inertia is the measure of what I'm writing over here in Hindi. The word is Urdu word of kahili. Okay, and we will discuss more about it, and we have almost finished with that. So every body continues in its state of rest or of uniform motion unless impressed by an external force. Now this force, okay, just I would like to provoke you. In nature, forces are of four kinds. And the weakest of all these forces is the force of gravitation. There are two forces which take place inside the nucleus. This one is called the strong nuclear force and the other is called the weak nuclear force. A strong nuclear force is the strongest force of nature. Next is electromagnetic force. And the third is the weak force, which is a very short range force. Nuclear forces are very short range forces. The gravitational force and the electromagnetic force are short range as well as long range. So these are the nature of the various forces. I will describe force again in the next lecture, where I take up Newton's second law and the Newton's third law. Okay, so that much. So long. Thank you very much.